Hello and welcome. I'd like to give you a short podcast today based on the presentation that I gave at the CEN workshop kickoff meeting in June 2013 in Brussels. The title of our workshop is Validation of Computational Solid Mechanics Models Using Strain Fields from Calibration Measurement Systems. And I'd like to give you an introduction to what we mean by validation and to start by why computational solid mechanics models are important to us. So I'd like to start off by talking a little bit about conflict resolution in this context. So as engineers, we're interested in designing structures, machines and components that are sustainable. So we want to increase the sustainability of our designs. We're also interested in safety and increasing the safety of the structures that we design. And then we're normally also interested in performance and increasing performance. So these are all things that we want to improve. And at the same time, we'd like to reduce the cost of whatever it is that we're designing. So if we take a personal transportation system, then when we're young, we would like a car that has the performance of an F1 racing car. And then as we get a little older and perhaps we have children, then we'd like to protect them in a vehicle that has the sort of protection around it that an armoured personnel carrier has. And then as we get older still and begin to get some grey hairs, then we start to think about the long-term future and preserving the environment for our grandchildren. And so the sort of performance that this Shell pack car has in doing many hundreds of miles per gallon is what we're looking for. And so as engineers, we end up with a compromise that might look something like this, the Fiat Punto. So engineering simulation is used to resolve this conflict between structural integrity, energy consumption, and cost. And the design optimization that we need to do in order to achieve this resolution of conflict is performed using computational solid mechanics models. Elegant, successful design depends on efficient use of materials and high credibility for our simulations. We can only achieve efficient use of materials if we have high credibility in our simulations. Model credibility is reflected by the willingness of persons to base decisions on information obtained from the model. That's a direct quote from some work that was done in the 1980s. So, in the presentation I did in Brussels, I asked the audience whether or not this model is good enough. Do they have credibility in this model? This is a very simple model of a compact tension specimen used in fracture experiments in my lab. And my students have put a strain gauge on the back face of the specimen and also conducted a finite element model of it. And they found that the finite element result gave them a strain of 245 microstrain. And they compared that to their experimental results. And they found that in the experiment, they got a result of 252 microstrain plus or minus 9. That's the standard deviation on a series of experiments that they did. And so I asked the audience there whether or not they thought that was a good enough model. And most people in the audience said, yes, it was. It was fine. So then I pushed their comfort zone a little bit further and said, would they buy this car based on this knowledge of the analysis done of the bonnet? So I've got two analyses here. If you follow the green arrows along the top, we have a finite element model of the structure of the bonnet. So I'm showing you in the middle diagram the mesh that was generated, and then on the extreme right, the strain distribution generated using that finite element model. And if you follow the red arrows down to a picture of the bonnet with a speckle pattern on it for digital image correlation, and then in the bottom right hand corner the DIC result showing measured strains, experimental strains from it, and a comparison has been done between the model and the DIC results. And so I asked the audience whether or not they would have confidence in this car and its damage worthiness or crash worthiness based on this result. And some of the audience were happy with it, some not. So not as confident as they were in the simple compact tension specimen. And so then I made it even more personal by asking them, would they have this heart valve implanted? And so this particular heart valve comes from the aortic position. So this is the high pressure valve that controls the flow from the high pressure side of the heart out into the body. And in the center, the bottom, is a picture of a fluid-solid interaction model of the valve and the flow. And in the top, I'm showing you the way in which it was validated by combining a video picture of the valve in a pulse duplicator in the left-hand half of the picture, and in the right-hand half, look at the equivalent finite element result. And then I've got a series of images from that video on the right-hand side, showing that the simulation roughly follows the video captured in the pulse duplicator, the benchtop experiment, if you like. And so then I asked the audience whether or not they'd be happy having this valve implanted, and almost nobody was happy with this level of validation. So we've got a decreasing level of happiness as we made the model more and more personal. So this raises the question of what is acceptable in finite element modeling. And if we go back to the very earliest philosophical writings on these sort of issues, Hume in 1748 suggested that observational evidence will never support any hypothesis about the unobserved. And that pretty much puts modeling and theoretical analysis out of business if we take that sort of approach in engineering. So a more pragmatic approach is required. So if we turn to Popper in the middle of the last century, he proposed that observational evidence cannot prove a hypothesis correct, but it can demonstrate its inappropriateness or its falsity. So that implies that there's always a possibility of making a mistake when accepting or rejecting a hypothesis, but it does give us some opportunity to work with models and with theories. So if we come a little bit closer to the modern day, then Rudner, talking about climate models, argued that the decision to accept or reject a hypothesis depends on the strength of the evidence. And our judgment on the strength of the evidence depends on the importance of making a mistake in accepting or rejecting the hypothesis. So for engineering models, the importance of making a mistake will be measured in economic cost and loss of life or injury resulting from an engineering failure. So the strength of evidence required to accept a computational model could be very high in some cases, for instance in the design of an aircraft or a nuclear power station. So that means that we need comprehensive validation of the model if we're to use it to design these sort of engineering structures. So what do we mean by the word validation? There's previous work in this area. There's something called the ASME VMV Guide. That's the American Society for Mechanical Engineers Verification and Validation Guide. And they define verification as the process of determining that a computational model accurately represents the underlying mathematical model and its solution. And they define validation as the process of determining the degree to which a model is an accurate representation of the real world from the perspective of the intended uses of the model. But unfortunately, they don't provide any methodology for establishing either verification or validation of a computational solid mechanics model. So we believe that we can use experimental mechanics for this, and that we can treat the validity of a computational solid mechanics model in the same way as we can a scientific hypothesis, and recognize that observational or experimental data cannot prove its validity. But increasing the body of evidence can increase the degree of belief in the model. So it's perhaps obvious that current practices based on a strain value at a single point are inadequate. Okay, maybe it's not so obvious. So here's an example of a finite element model of a turbine blade. showing us a nice hot spot in the bottom right-hand corner. And this was done by a company called Snecma in France. And when they did some tests, they discovered that the blade didn't break at this location. And so we were asked to do some experimental measurements on it. And so here's a photograph showing our experimental setup. We used reflection photoelasticity. We put a coating onto the blade, excited it with an air jet across the tip, which you can see in the right-hand side of this photograph, and then viewed it using a photoelastic polariscope and strobe illumination. And that allowed us to use phase stepping to obtain numerical data about the strain distribution over the surface of the turbine blade. And so here's our photoelastic result. We obtain it in terms of the difference in the principal stresses. And you can see that we've got a small hotspot in the same place as the finite element was predicting, but a much bigger one on the right-hand edge of the blade, which the FE model had not detected at all. And so if you had validated the finite element model by simply putting a strain gauge at the location of the hotspot predicted by the model, you would have probably determined that your model was fine, when in fact it wasn't. So, although it may be obvious when you think about it that we need to do full field measurements, we often don't do it. And that's probably because this obviousness is overpowered by the cost of getting experimental data, which to some extent has been alleviated by new technologies such as the digital image correlation techniques that are becoming ubiquitous, digital volume correlation, electronic speckle pattern interferometry, and thermoelastic stress analysis. The other factor that's made it difficult to validate using the whole field of data is the lack of methodologies for quantitative comparisons of the data. And this is because we often get our model data and our experimental data in a different orientation, a different coordinate system, at different scales, and also with different pictures of data. And recent work has shown that we can resolve these issues using decomposition. And I'd just like to talk a little bit about decomposition of strain data. So modern digital image correlation gives us huge data sets, typically of the order of 10 to the 5 or 10 to the 6 pieces of data covering an area of the specimen. So here's a simple example. This is a composite tie bar with a slot in it being loaded in tension. On the left-hand side, you can see a picture of it in a test machine with a 3D digital image correlation system set up to record the data. And on the right-hand side, I've shown a simple finite element model of the same bar. And we're going to look at a small area at the tip of the slit here. So I'm going to extract data both in the experiment and in the finite element model. And here are the two sets of data. On the left-hand side is my experimental data. On the right-hand side, the finite element model. We can decompose, let's use the experimental data first of all, decompose this data using Chebyshev polynomials to get a set of Chebyshev moments, which are plotted here, first 20 moments. And these moments completely describe the experimental data. We can reconstruct the experimental data using the moments and the original polynomials. Here's my reconstruction. And if we do a simple correlation using the MATLAB code, we can look at the degree of agreement between my reconstruction and my original data. In this case, it's 1. It's essentially perfect. If we do the same process for our theoretical data, our model, then we get a set of Chebyshev moments, first 20 moments again to represent our finite element distribution. Reconstruct to check that it's a good representation, and in this case it's 0.9897, so effectively 1, so it's a good reconstruction. So we've now got two sets of Chebyshev moments, one representing our experimental data and one representing our finite element data. We've reduced our massive data sets from the order of a few thousand data points down to just 20 values each. And we can compare these two sets of values on a simple chart here. So I've plotted on the y-axis the finite element Chebyshev moments, and on the x-axis the Chebyshev moments from the experiment. And if the two sets of data agreed perfectly, they'd all lie on the 45-degree line. But of course, there's some uncertainty, some errors in both sets of data, and so we wouldn't expect them to agree perfectly. And so we've quantified the degree of agreement that we might expect by plotting the uncertainty in the experiment. So that's what my dotted lines are on the graph. The red line is the 45-degree line for the perfect comparison, and the green line is the regression line through the data points. So the question then becomes, how wide should we make this band of uncertainty within which we'd expect our data to fall? So we've defined this bandwidth as twice the uncertainty in the experiment, or the uncertainty in the experimental feature vectors. And this uncertainty is made up of two components. The first component is the uncertainty that we can measure by calibrating our experimental system. We call this a calibration uncertainty. And the second component is the uncertainty that arises from using the image decomposition process. And we've put some limits on this. We've said that this uncertainty must be less than the uncertainty that we carry from the experiment. And in addition, we must have no cluster that is bigger than 0.3% of the total number of pixels with a value greater than 3 times the uncertainty. So that's my second condition, B there. And so those two things together allow us to define this uncertainty zone. And we can say that a model is valid if all the points plotted on the graph in the center here lie within this uncertainty band. And so as part of the Vanessa project, we're performing a round robin, as it's sometimes called, or an interlaboratory study to give its formal name. And so we've developed a protocol for using this validation procedure, a draft document that you can download from our website that gives you the option to conduct a validation experiment or simply to use our data fields and to perform the analysis that I've just shown you on the previous slide, and then to comment on the validity of our model. So we've provided 3 different data sets, an antennae intended for use in space, a rigid wedge in contact with a soft material block, fairly difficult contact problem, and then an I-beam in bending that's applicable to a wide range of industries, including aerospace and construction and so on. So we've published that protocol through the Vanessa and the CEN website, and you can participate in our project by performing the validation procedure and giving us feedback on the protocol. So let me just say a few words now about CEN Workshop 71, or nicknamed Vanessa, and why we're doing it. There are a large number of benchmarks around for verifying finite element packages, particularly those provided by NAFEMs. And when you buy a finite element package, you would hope that the vendor has already verified that it's solving the appropriate equations in an appropriate manner. But there's very little support for validation and almost no process described to allow you to do it. The ASME V&V guide tells you what needs to be done, but not how to do it. And so with the CEN Workshop 71, we aim to plug this gap by providing a general approach to validation of computational solid mechanics models, particularly aimed at engineering design and the evaluation of designs for structural integrity. Thank you for listening to our podcast today, and there's a series of 2 other podcasts that you might be interested in listening to on this website. Thank you. Bye-bye.